Hey guys, welcome to Steven's physics class. Today we're going to go over capacitors in series and in parallel. To start today, we first want to talk about what a capacitor is. So as we can see here from this definition, a capacitor is two charged metal plates that are separated from each other by a piece of paper that can store charge when connected to a power source. So basically capacitors are used as devices that can store charge. They're often used in different electrical devices and in circuits and things like that. They're very useful in computers. And so the first example that we want to look at here today to kind of understand capacitors and what they do, how they work, is just a simple circuit. So here we see it's just a simple circuit of a battery right here that's being hooked up to a capacitor, which is right here. And so this battery is providing 12 volts, and each capacitor has a capacitance, as we can see from this equation right here. And that capacitance is just the amount of charge that each capacitor can hold. And so if we want to figure out the charge that's being put into this capacitor, this particular one, we can use this equation, which is Q is equal to V times C. So Q is a charge, and then V, as we can see, is voltage, and C is capacitance. And so for this particular capacitor in this simple circuit, we know that Q is going to be equal to V, the voltage, which is 12 volts, times C, which is the capacitance of 6 farads. And so when we multiply this out, we get that our Q here is 72, and this is measured in coulombs. So for this simple circuit, this particular capacitor is able to hold 72 coulombs of charge, or 72 coulombs of charge is going through it. All right, so now that we understand this first example of what's going on, we want to look at the second example of when we put capacitors in series. When we put capacitors in series, basically what we're saying is that we're putting the capacitors side by side to each other. And when we do this, it means that the voltage between each of these capacitors is not the same. And so in order to account for the charge going across the whole circuit here, we need to be able to add these capacitors up and basically make it so that they're just combined as one overall capacitor. And so in order to do this, we need this equation here, which is 1 over capacitance is equal to 1 over capacitance of the first capacitor plus 1 over the second one plus 1 over the third one. And so let's look at this first example here. We have 1 over the capacitance, which will be our total capacitance for the whole circuit here, is equal to 1 over the first capacitor, which is 6 farads, plus 1 over the second one, which is 12 farads, plus 1 over the third one, which is 4 farads. And now when we add all these up together, I'll just do it for you, but we will find that the number here would be 0.5 farads is equal to 1 over CS. Now, when we rearrange this equation, we would get that the total capacitance going through this whole circuit is 1 over 0.5 farads. And we calculate that to be 2 farads over the whole circuit. So now that we found this, we can use this equation once again. Q is equal to V times C to be able to find the charge that's held throughout these three capacitors. And so once we do that, we have that Q is equal to the voltage, which is 18 volts. And now this voltage is the same throughout the whole circuit, because we've added all these together to just basically make it into a simple circuit. So we could even redraw this to be this battery source here of 18 volts being provided to a capacitor, to a single capacitor that holds 2 farads and has a battery source of 18 volts. So once we do that, we say 18 volts times the capacitance of 2 farads would be equal a total charge of 36 coulombs. And so now we can see that when we add capacitors in series, it actually decreases the amount of charge that they can hold across the whole circuit rather than increase, as we will see with parallel. Okay, so now let's go ahead and look at some capacitors in parallel. And so really the big difference here between in being in series and in parallel is that the voltage across these capacitors in parallel is going to remain constant. And so this means that we can actually just add up all of these capacitors together in order to find the total capacitance. And so even if we wanted to, we could just find out the charge that is going through each one of these capacitors. So we could take this first capacitor, for example, that has a capacitance of 2 farads, and we can just use this equation, Q is equal to VC, and we can take the first capacitor is equal to 2 farads times the voltage of the battery of 12 volts in order to find the Q, or the charge of 24 coulombs. And now what we could do is we could just add all of these values together, find them of each capacitor and the charges going through them, because they're all going to be different. And we could just add them all up together and find the total charge. Or we could just find the total overall capacitance by using this equation, adding them up to find the total charge going throughout this whole circuit. And so to do this, we use this equation of the total capacitance is equal to the first capacitor plus the second plus the third plus the fourth, and so on, just like before. And so in order to do this, we just say that the total capacitance is equal to the first one, 2 farads, plus the second one, 6 farads, plus the third one, 4 farads. And in order to find that the total capacitance is 12 farads. And when we do this, now we can find the total capacitance for the whole circuit using the same equation that we did to find the charge for just one capacitor, and Q is equal to VC. But in this case, we'll use the overall, which we will find is still 12 volts, but this time we're multiplying it by 12 farads, because that's a total capacitance. And so the total charge that this whole circuit can hold is 144 coulombs in this example. The last example now that we're going to look at today is when we combine with capacitors in series and in parallel. So as we can see in this example, we have capacitors that are in series and capacitors that are in parallel. And so our strategy in this is basically going to be the same, is we want to be able to create a simple circuit to where we can add all of these parallel and series examples together to make it just one single capacitor that will be across the whole circuit. And so in order to do this, first we're going to look at these capacitors in parallel. And what we're going to do is we're just going to add them up to make them a single capacitor. And we did this before. This part is pretty easy. So we just use that same equation of capacitor in parallel, which is capacitor 2, 3, and 4 added together. And so we're going to do that. Capacitors in parallel is equal to 2 farads plus 4 farads plus 2 farads, which is going to equal 8 farads for that particular 3 capacitance in parallel. So now we could even rewrite this again to put this all in series now to make it the single battery source of 12 volts. But now we have 3 capacitors in series. Okay, 12 volts, but now this middle capacitor is 8 farads, and this first capacitor is still 8 farads, and the other one, the third one, is 4 farads. And so now we can add these up together in series like this. And so for this equation, or we're going to use this equation of 1 over series capacitance like we did before. So we'll do that here. 1 over the capacitance in series is equal to 1 over the first capacitance, which was 8 farads, plus 1 over 8 again, farads, plus 1 over 4 farads. And this will give us a total of 0.5 farads. And so, again, we'll use this equation just to show how that works. And we'll rearrange the equation real quick to make CS is equal to 1 over 0.5 farads. And so the total capacitance in this series would be 2 farads. And so, once again, we can use our equation Q is equal to VC to be able to find out the total charge going throughout all of these capacitors. We take the total voltage, which is 12 volts, and this now works because the voltage is the same over one singular capacitor, because we've basically made this whole circuit into a simple circuit, because we can now, I'll just draw it again real quick, look at this 12 volts as if it was like this, and it has a single capacitor, which is 2 farads. And so since we can look at it like that again, we can just make it 12 volts times the 2 farads of the single capacitor, and the charge then would be Q is equal to 24 coulombs as our total charge going throughout this circuit. And so that's it for today. Thanks so much, guys, for tuning in.